All right. So chapter 9.1, we'll spend 3 days on this, kind of dividing that up. Yeah, 9.1, not 3 days, 3 lessons on it. We'll do 2 lessons on our block day. Just setting up and introducing the different tests that you're going to need. So Edson, are you typing on mine or did you make a copy? Because I still have you sitting on my version. Or do you have both open maybe? Okay.
I did make a copy, and
Okay.
it was showing me on the top as the only one.
All right. Okay, go ahead and go to the first slide. So you should be familiar now with this expression, the way we set up the different terms. We introduced the idea of a series. A sequence being something that's just commas, a series being that the terms are actually added together. So we add them together, and then we call the last term the nth term. We don't specify which term it is, it's just called the nth term. So if you understand that the last term is the nth term, then that leads us to something called the nth term test. Here are some key questions. For every series you have, you're going to be asked to determine, does the series converge or diverge? And if it converges, can you tell me what it converges to? Sometimes you can. Sometimes you can't. Sometimes it actually converges and settles on a number. Other times, all we know is that it does converge. We just don't know specifically what it's going to converge to. These are key questions. That is going to be the bulk of all of chapter 9 is being able to answer those questions about infinite series. This is similar to what we talked about yesterday. If you're given the infinite series that alternates between 2 and -2, what does your gut tell you about whether or not that converges? You think it converges to 0? Okay. All right, anybody else? Have an intuition, a spidey sense that's tingling a little bit? It alternates. Okay, so then will it converge or diverge if it alternates? We talked yesterday about what alternating means. No, it's a special form of either convergence or divergence, one or the other. Anything that alternates? Okay, this is going to diverge. All right, by definition, it cannot converge. So let's look at what its sum is. All right, let's look at S sub infinity. Okay, this is not an integral S. This is actually the letter S, but not an integral S, so be careful about that. Now, and remember, when an integral, you put your bound kind of on the other side of the lower part of the integral symbol. This is going to be definitely on the right side as a subseries. All right, what is the first sum? If you just add the first term. The first term, 2. Okay, now add the second term to it. What are you going to get? 0. Then add the next term to that. What do you get? 2. And the next term to that. 0, 2, 0, etc. Okay. These sums alternate, the first sum, the second sum, the third sum, the fourth sum, these partial sums, they do alternate between 2 and 0. It bounces back and forth. Sometimes we call that oscillating. Another word is alternating. It is alternating and will not converge. So if it's not converging, we say that it does diverge. So this is a divergent series. Because the terms, or we call them the partial sums, alternate. But it would be helpful to have some actual tests, say tests we're going to give names to that we can cite as good reasons for justifying what's going to happen. Okay, so let's kind of think about this one too. This is similar to one we saw yesterday. Does this series, it's an infinite series, the numerator is going to always be 7, the denominator will always be a power of 10. Will this converge or diverge? Okay, Kaylin, do you have a sense, a gut, what your gut tells you? Is this going to be a convergent or divergent series if you add up the terms as you go?
Divergent.
Divergent? Okay, what makes you think that?
Because you keep adding a number even though it's getting smaller all the time.
Okay, so you're adding small numbers, but you keep adding, so it's getting bigger and bigger and bigger, okay? Anybody else have a thought on that? Alex? You think it's converging. Why? We keep adding something. Isn't if you add something, it always going to get bigger? Until what's zero? Near zero, okay.
Is this like the ones where it's like converting to 7 over 9? Because it's just going to be 0.7, 7, 7, 7, 7.
Yeah, yeah. So it's getting bigger and bigger and bigger, but is there a limit to how big it will get? And the answer is yes. Okay, the limit to how big it'll get is 7/9. Even though it will continue to get bigger and closer to 7/9, it will just never actually get over 7/9. So you're exactly right. The first one was 0.7. The next sum, the second sum, would be 0.77. The third sum is 0.777. And on and on and on. 7 over 10 to the nth, okay, as we're going. But that is approaching because it's 7 repeating. The fraction for 7 repeating is 7/9. So this is a convergent series because it has a boundary, a ceiling. It'll get closer and closer and closer to that. It'll just never get over that. So we say that that is the value of its infinite sum. This is convergent. So it's interesting how both arguments can be true. Kaylin's argument is that it always gets larger is true. Alex's comment that it's getting larger, but the amount it's getting larger by is getting smaller. Each time you add, it's adding a smaller amount. And then Edson finally landed on, it's getting larger by an incrementally small amount, and it will never get beyond 7/9. All right, that leads us to a test of divergence called the nth term test. In geometry, back in the day, you guys took geometry in what, 8th grade? Okay, was that COVID? Start of COVID? Yeah, spring of 8th grade. Who did you have? Mrs. Brannon, okay. 10 people. Who are we missing that used to be in that class?
Yeah, 2 of them are like professional football players now.
Oh.
Basketball. One used to go here in the Bradner is
Kennedy.
I remember Wyatt went.
All right, so who did we gain? We gained? Oh, these, so you guys didn't go, you went to a different school other than Valley Christian. Okay, anyway. In geometry, you learn about if-then statements. All right? So let's quick review some if-then statements. All right. If A, then B. Okay, so if this, then that. So you start with that. Do you guys remember what this is called? Okay, this is called the converse. Very good. Okay. All right, what other formats of these statements can you take? Jonathan? Let's see if we can, how else could you do that? Besides just switching them around. Do you know what this is called? contrapositive statement. Okay. All right. And then you could do, if not B, then not A. You could also do the converse of the contrapositive. All right. Are you guaranteed truth all the time? Okay, like if I say, assume statement, the first statement is true. Does that mean that the converse is true? Okay, so for example, if it's raining outside, the cement will be wet. Okay? What would be the converse of that statement? If the cement is wet, then it's raining outside. Is that a true statement?
No.
No, because are there other reasons that the cement could be wet?
Still the drain.
Okay, the sprinklers hit it, whatever, okay?
Water.
All right, how about this? If it's not raining, then the cement is not wet. Is that true?
No.
No. Okay. So just because the first statement might be true doesn't mean the other ones are. Okay, so that gets to this. If, this is our A part, if the infinite series, denoted A1 to AN, converges, then the limit of the last term is 0. That is a true statement. We start with that. The contrapositive is also true. So, if the limit of the last term is not 0, then the series must diverge. In other words, not converge. That's the contrapositive. If not A, then not B. Okay, we've got that going on. However, the converse is not true. Just because a limit might happen to be approaching 0 the last term does not guarantee convergence. The only thing that is true that you've got to walk out of here with the understanding of is this statement right here. The test that we're going to be talking about only guarantees divergence. It does not guarantee, it's the only test that you can only tell one thing from. The infinite series must diverge. Okay, so switch over to your list. And on the nth term test, you want to put, if the limit of the last term, or the nth term, is not 0, then the series diverges. If the limit of the last term is not 0, the series must diverge. But you have to be so careful that you don't assume the other part to be true. You cannot assume that if the limit of the last term is 0, it might converge, but it might not. There's no guarantee. And so many students fall trapped to thinking that the one presupposes the other, and that is not true. Only if the last term is not 0, then we have divergence. Let me show you, so I'll switch back to your notes. Will this converge or diverge? All right, that is the question. So we're going to apply the nth term test. Oops. In the nth term test, you take the limit of the last term, which would be -1 to the n, as n approaches infinity. What is the result of -1 to the n as n approaches infinity? Well, what are the possibilities? Okay, is infinity an even number? If it's an even number, then it would be +1. Is infinity an odd number? If it's an odd number, then it would be -1. Either way, we don't know if infinity is even or odd, but either way, what are the only options? -1 and +1. Since the only possible outcomes are 1 or -1, we can be assured that it won't ever be 0. That's all you care about. All you care about is proving that it's not 0. You don't care about proving what it is. You only care about proving what it's not. So since I proved that it's not going to be 0, what's the conclusion? Then it diverges. Since the limit as n approaches -1 to the n will never be 0, the series, whoops, that was poor. Must diverge. That is your conclusion. So again, I just can't emphasize that enough. If you're only trying to prove what it's not, you're not trying to prove what it is. Okay, only what it's not what it is. Okay, here's another one. Will this series converge or diverge? Okay, well, we want to apply the nth term test. It's always helpful, too, for you to sort of announce which test you're trying. So I usually get in the habit of saying what I'm going to try. So the limit as n approaches infinity of the fraction 3/10 to the n. That will be the fraction 3/10 to the infinity. That will be 3 to the infinity over 10 to the infinity. What's the result of that? Careful. Which denominator is bigger? Or which term is bigger? Denominator. If the denominator is bigger, okay, so this is going to approach 0 because the denominator is larger than the numerator. So what do we conclude? Because our limit test gave us it was equal to 0. Does that mean it's convergent? What does it mean? Okay, so this is inconclusive. We cannot conclude for certain the convergence or divergence. It might be, it might not be. So since it is inconclusive, then we need another test. And so bring on now our second test of the day, which is called the geometric series test. Yes, sorry. Got it? Okay. All right. So a geometric series, by definition, is based on what kind of mathematical property? If it's geometric. Multiplication. All right. So this is a pattern of multiplication by the constant r. So if you recognize that this is an R pattern, it's multiply, 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 we call it geometric. So now we have some if-then statements here. If R as an absolute value is smaller than 1, then we have convergence. And in fact, we have such strong convergence that there's a convergence formula for it. So we have convergence that leads right to that formula. If R as an absolute value is larger than 1, then we have divergence. Another way to think of that, if you're thinking of absolute value, you can just say if r is between 1 or -1, then the series will converge, and it has a specific convergence formula. So this is beautiful. So I'm going to have you add this to your geometric, to your list of tests, not right now, but later I want you to go back and add this one. So I want us to test this out. Tell whether each series will converge or diverge. If it converges, give its sum. You can recognize that this is going to be a geometric series because it has parentheses in it and raised to a power. This power produces a geometric pattern. Okay, so focus on that. If you're not 100% sure, then plug and chug. You're going to get 5 plus 5 halves plus 5 fourths plus 5 eighths plus 5 sixteenths plus ... You should be able to pull out what the pattern is being multiplied by every time. Do you see what it is? 1/2. Okay, multiplying every time by 1/2, 1/2, 1/2, 1/2, 1/2. So r is equal to 1/2. Since r is between 1 and -1, the geometric test tells us we can conclude that the series will converge and it's even stronger than just saying it converges. It's going to converge to the formula a sub 1 over 1 minus r. So a sub 1 is the value of the first term, which is 5. 1 minus r is 1 minus half. So that's 5 over half, which is 10. So that means that this series, as a sum, if you add up all the terms, will get up to 10 and will never cross 10. It will never be more than 10. We're approaching 10. That is true because the r factor was between -1 and 1. Okay, here's another one. We recognize this, again, as a geometric series because it's got the power and it's got the fraction. And we can tell that the terms are going to be 3/5 plus 9 25ths plus 27 125ths plus 81 625ths ... Now, what will happen when we we recognize that this is geometric and the r is 3/5. So again, since r is between those two values, then we know that the series will converge. And in this case, it will converge to a1 over 1 minus r. The a1 in this case is 3/5 because it's the first term. And 1 minus 3/5 is the r. So that's 3/5 over 2/5. And 3/5 over 2/5 is 3/2. And so this series, if you add up all the terms infinitely many, you'll never get more than 3/2. 3/2 is your upper limit, your boundary that this series is going to converge to that sum. Okay, this one. Is it, I'll tell you, it is geometric, but can you tell me what the r pattern is? What's happening every single time? What's it multiplying by? The numerator is multiplying by pi, and the denominator is multiplying by 2. All right. Is pi halves between 1 and -1? Well, what's the value of pi? More than 3. And you divide that by 2, you get still more than 1.5. So since r is greater than 1, the series must diverge. So it doesn't converge at all. The series will diverge if you've identified r as being pi halves.